Hello, my name is Andy Schweitzer, and this is a quick little video on the introduction for acids and bases. The first question is what makes something acidic? This is a pretty important question here, and in the end, H3O plus ions, this is called a hydronium ion, is what determines whether something's acidic or not. When they were first identifying this was a active participant, they thought it was an H plus ion. So that was commonly used to show an acid, and these are now still interchangeable, but if you write down H plus, it really means H3O plus. For a base, it is going to mean an OH negative. The name of this guy here is called the hydroxide ion. The hydroxide ion spelled like that is again what our base is. I will say that in a solution, if you have greater amount of hydronium ions than hydroxide, then your solution will be acidic. If you have equal amounts, then you will be neutral. If you have more hydroxides than H pluses, you will be basic. Pretty straightforward. As we move on, next question would be, okay, if we know that these guys are in fact causing us to be acidic or basic, how do we actually go about making them? Or next question might be, I guess making it, that'd be the best question at this point, okay? So an acid is anything that can produce this H3O plus ions, or technically it would be something that could remove hydroxides. A base is anything that can produce hydroxides or technically remove H plus ions. So for an acid, okay, this is called a hydrolysis reaction. So acids and bases are different as to how we can actually make H pluses or hydroxides. So pay attention here as we move along. Really the only way to make an acid is for some sort of acid, I'm going to say generic HX, to react with water. Okay, it will dump its H onto this guy. In fact, it's going to be an H plus, meaning it left its electron behind with the X, with the anion. This is a cation anyways, but either way, and the result of this guy is going to be H3O plus, and then the anion is just been all by itself. This is called hydrolysis. It really is the only way that we can get an acid to produce H3O plus ions. This thing by itself is not acidic. Therefore, it needs to have water to dump its H onto to get the actual acid counterpart. This is why earlier on in the acids, when we learned to name them, we wrote HCl as an aqueous compound, because technically without the water, it's simply not going to have the ability to produce these guys. It's missing part of the main component. So HCl, and you can just say plus H2O yields H3O plus ions and Cl minus. This is the means by which HCl produces acid right here. This might be considered our acid, but in reality, this is what actually does the work. Now, a base would work a little bit different, okay? In this case, a base needs to produce hydroxides. I'm going to show two different ways in which this can happen. First one is I'm also going to be showing is the hydrolysis version, okay? And this is very similar, but let's just say, for example, X negative, okay? reacts with water, and in this case the water will give the H away. In an acid, the water accepts it. In a base, the water donates it. This is going to be HX plus OH negative. Now, this was negative to begin with, so when it gets the H plus, it happens to neutralize down to no charge. But in a sense, this is still +1, -1. And now my base is here. Water is acting, in this case, as a donator, in this case, as an acceptor. So something that can both donate and accept, go both ways, act like an acid and like a base, we call this particular property this is a P, teric. Okay? Can act both like with the acid reaction and with the base reaction, either way. So in this case, this is one means by which we can produce hydroxide ions. All right, the second option would be with a ionic salt, simply dissolving. An example would be NaCl. You should be aware that when an ionic salt dissolves, it produces Na plus ions and Cl negative ions. Now in this case, there's no hydroxide present, but it would simply produce these two cations, and so this technically would be neutral. But if I had the salt NaOH, this is +1, -1. When this thing dissolved, Na plus ions and OH negative ions. All right. As we increase our concentration of hydroxides, and therefore this would be a very much basic substance. Now, as something dissolves like this, the level of basicness of this thing would purely be based on the solubility of this substance. Sodium hydroxide happens to be very soluble. Anything, in fact, that contains the sodium as a cation is very soluble. But if we were to use, let's say, iron hydroxide, hydroxides generally are not very soluble. So this thing, when it dissolves, yeah, it will produce some iron 2+ ions, and it will produce some hydroxide ions, but the extent to which this particular substance moves in this direction to produce products is very small. And therefore, we get a very minimum amount of hydroxides, and therefore most of our stuff stays here, and this thing's not really that basic. Produces some hydroxides, but just not very many. Okay. Can hydroxide ions and hydronium ions exist together? This is an interesting concept, and as analysis of acids and bases were existing, we have this situation where we discovered that water, I'm going to flip back to my black, H2O, two of them for that matter, go to, in solution, we found that in solution they produce H3O plus ions and hydroxide ions. This is called auto-ionization. Now, scientists believe that this is taking place all the time, that in solution we have a beaker, and even though we don't realize it, there are water molecules in here, and lots of them for that matter. I mean, I couldn't draw enough of them to show a correct proportion. Very, very small number of these things are converting from water over to H3O plus ions. I'll put that in this color, H3O plus ions, and then some of them are producing into hydroxide ions. Very, very small amount, okay? But turns out that this is called an equilibrium system. It's going back and forth. And if you were to write out an equilibrium expression for this thing, you'd find out that, okay, well, this is a pure liquid, so it doesn't have a concentration. So the K value for this, which is telling us the extent to which it goes to product, is equal to the concentration of the products and the concentration of the hydroxide ions. Turns out that at 25 degrees Celsius or 298 Kelvin, these two values cannot, when multiplied together, the concentrations will not exceed K equaling 1.0 e to the negative 14th. So, like I said, this thing, there's not a whole lot of concentration here. We call this value Kw, by the way. All right, so together, these two concentrations cannot exceed 1.0 e to the negative 14th. And that, regardless of whether we have lots of hydroxide or very little, lots of H pluses or either one together, they cannot exceed this value. So can they exist together? Yes, but only in small quantities, okay? So if we have equal quantities, then we would be neutral. Again, as these auto-ionize, we don't notice any changes in acidity pH because they're equal. Okay, this is going back and forth. But if, again, any water solution, this is happening, and if it's pure water and it's happening, then we get equal quantities of these, we would have the concentration of the H3O plus ion would equal the concentration of the hydroxide ion, and that would be 1.0 e to the negative 7th. That Now, one important thing to remember is that, again, if they are equal, it's neutral. So this is an important value here. To me, it's a good mental note. Anytime I have an acidic solution, my concentration of H plus ions must have risen above this midpoint, greater than 1.0 e to the negative 7th. If I am basic, for that matter, that means that my high H plus ion concentration, again, had to drop below that value. Conversely, on the top one, the hydroxide ion must have fallen below that midpoint, and in this case, the hydroxide ion must have gone above this value. There are two, they're locked together. They teeter-totter each other. In fact, anytime you are given either one of these guys at equilibrium, you would be able to plug in this value and solve for the corresponding value. So that's pretty much about it. We will at this point be looking for a little bit of talk on pH, and that'll be our next video.